precipitation on the slopes of the Serra do Mar, bringing on landslides. Communities had to be evacuated. Many observers thought Cubateo the most polluted place on Earth, a title with many claimants. After much dithering and denial, authorities responded to media harassment, citizen protest, and several deadly industrial accidents, especially after military rule ended and questioners of the state development model grew less fearful. Under the impact of regulations, fines, and new technologies, pollution levels began to drop in 1984, and by 1987 came to only 20 to 30% of their previous levels. By the late 1990s, trees had returned to the slopes above the city and carp swam in the effluent pools of some of the chemical factories. The air of Cubateo was no worse than São Paulo's, which is to say it was bad, but much better than it had been. In Cubateo, the modernizing state created the industrial pollution. When democratized and duly pressured, it also tamed it. 71. Ankara and Cubateo addressed air pollution problems within 20 to 30 years of their first major appearance. London and Pittsburgh appear laggards by comparison. But relative to Mexico City or Calcutta, Ankara and Cubateo posed easy problems. Neither city had to regulate cars, infringe customary rights, or impose sacrifice on its citizenry. After 1950, more and more people lived in more and more cities, like Mexico City and Calcutta. In 1988, the WHO estimated that of 1.8 billion city dwellers in the world, more than a billion breathed air with unhealthy levels of sulfur dioxide and soot or dust. 72 the kind of civic, scientific, and political synergies that helped London, Pittsburgh, and dozens of other cities in Western Europe, North America, and Japan to clean their air proved elusive in the megacities. They were growing too fast. Civic responsibility suffered, as many citizens identified more with their villages of origin than their city of residence. Law and regulation, even if on the books, proved hard to enforce. Economic development took precedence over other concerns. Perhaps most important, growth at such rates spawned any number of social pathologies that menace the health of the poor and the security of the powerful. In this climate, reducing air pollution did not merit attention, effort, and resources. And so from Buenos Aires to Beijing and from Caracas to Karachi, urban air pollution clouds continued to gather. Chapter 4. The Atmosphere, Regional and Global History. This is the common air that bathes the globe. Walt Whitman, Song of Myself. The histories of urban air in the 20th century were variations on earlier themes. In the case of Mexico City or Athens, pollution intensified. In the case of London or Pittsburgh, it abated. Regional and global air pollution, on the other hand, had scarcely existed in prior centuries. Regional air pollution since 1870. Domestic hearths never, and cars rarely, caused noteworthy regional air pollution. That required the large-scale combustion of heavy industry generating pollutants that would hang around in the air for days or weeks. The main pollutants responsible for regional-scale air pollution, sulfur dioxide, particulates, and nitrogen oxides, have residence times that allow them to stay aloft and spread with the wind. Regional air pollution grew acute where heavy industry enjoyed high prestige and political clout, where the objections of the landed interests counted for little, where dirty coal was the cheapest fuel, and wherever large-scale smelting took place. In cases, a single smelter sufficed. The Second Industrial Revolution required plenty of copper, among other raw materials, and propelled a surge in copper mining and smelting in Spain, Chile, Japan, North America, and eventually Southern Africa. In Spain, the Rio Tinto mines, worked intermittently since Phoenician times but upgraded by new, British owners in the 1870s, soon yielded vast quantities of low-grade copper ore and all the sulfuric acid needed by Europe's emerging chemical industries. Or was smelted on the spot, roasted over charcoal in open-air piles, drenching the vicinity in sulfuric acid rain. A British commercial agent acknowledged, throats and eyes are painfully affected and all iron corroded out. Under these conditions vegetable life is impossible and animal life is rendered difficult. Pollution from Rio Tinto smelters welded miners and peasants and their families together in one of the pivotal moments in Spanish labor history, a strike against the British mine owners in which 45 people were killed. Here pollution united whole communities, a characteristic of the industrial labor movement of the pre-1914 era. But the scale of pollution and protest remained modest. In the 20th century, nickel joined copper as a key component in industrial and military production, and the scale of smelting dwarfed the efforts at Rio Tinto. The nickel-copper smelters of Sudbury and the copper smelter near Ilo produced poisonous airborne plumes that affected vegetation and lungs for miles around. Sudbury's open roasting smelters created a blackened desert between 1888 and the 1920s, when the first smokestack was installed. Nearby farmers complained to little avail until 1972, when a smokestack taller than the Eiffel Tower began to disperse sulfur emissions over a broader landscape. The Ilo smelter opened in 1960, and within 4 years, farmers up to 200 kilometers away had organized a lawsuit seeking compensation for crop damage. More damaging still were the Norilsk nickel smelters in northwest Siberia, part of a giant metallurgical complex built by Gulag labor after 1935 and run by Stalin's secret police. Norilsk grew to be the largest city in the world above the Arctic Circle and a bulwark in the Soviet military-industrial complex. Its pollution killed or damaged a swatch of taiga forest half the size of Connecticut and filled residents' lungs, contributing to severe health problems even by the standards of the late Soviet period. The men of Norilsk suffered the highest lung cancer rates in the world. In the 1980s, the smokestacks of Norilsk spewed out more sulfur dioxide than did all of Italy. Other Russian nickel smelters in the Kola Peninsula spread acid rain across northern Sweden and Norway, as well as east to Murmansk. What a single smelting complex could do badly, a cluster of heavy industries could do worse. From the late 19th century, several such clusters emerged, sometimes from state policy, sometimes from the juxtaposition of coal, ores, and markets, and often from a mixture of the two. These great industrial regions, the engines of 20th century economic growth at least until 1975, all produced enormous amounts of air pollution. The Ruhr and the sulfuric triangle make an interesting contrast, showing the impact of politics on pollution. The Ruhr. The Ruhr region in Germany is small as industrial heartlands go, about 1,500 kilometers, but beneath it run some of the world's biggest coal seams. It lies to the east of the Rhine athwart the Ruhr and Emscher rivers. In 1850, it was an agricultural area. By 1910, it produced 110 million tons of high-sulfur coal, employed 400,000 miners, and sustained the giant steel and ironworks of Krupp and Thyssen, both crucial firms in the German military-industrial complex. Industries so important to the German state escaped almost all regulation, so air pollution, smoke, soot, sulfur dioxide attained gigantic proportions. In 1900, the Ruhr was the biggest industrial region in Europe and probably the most polluted. Without it, Germany could scarcely have fought World War I. International events made clear the extent of Ruhr air pollution in 1923. Furnaces went full blast during World War I, but in response to Germany's failure to pay war reparations, French and Belgian troops occupied the Ruhr in early 1923 and strikes shut down industry until autumn. Suddenly the skies cleared. Local harvests improved by half. Trees grew faster than before or after. Women enjoyed a respite from dusting homes twice a day. But the French weren't getting the coal they wanted, and Germany's currency was losing all value as the government printed money to support the strikers. The situation proved intolerable for both Berlin and Paris, so negotiations ended the strikes. Work and pollution resumed. Official inquiries into pollution, perhaps inspired by the bright summer of 1923, followed. But they concluded that pollution was inevitable and that the Ruhr must adapt to it rather than try to limit it. Pollution reached new heights in the 1920s with new combustion technologies that permitted the use of lower-quality coal. One new plant, in Solingen, covered its surroundings in white ash within hours of firing up its boilers in 1929. Protests resulted in the installation of metal filters, but acidic gases disintegrated them within days. Even with better factory filters, Zolingen's air was unfit for young lungs. Its school had to shut down for 18 months to accommodate industry. Attitude, policy, and law followed this general pattern in the Ruhr because industrial firms and workers dominated the area from 1880 on. Profits and jobs mattered more than pollution. Farmers, landowners, housewives, and others whose interests suffered could not compete politically with Krupp, Thyssen, or the industrial unions. Profits, employment, and pollution burgeoned with Nazi rearmament after 1933. The Nazi affection for German blood and soil did not extend to German air, and certainly did not justify constraints on heavy industry, least of all during World War II. In 1944-1945 the Allies made Ruhr factories a special target, and although they found Ruhr smoke and haze made their bombers far less accurate than elsewhere over Germany, they eventually leveled a large share of Ruhr industry. German defeat in war once again led to a momentary relaxation of pollution. But with the Cold War, recovery of the Ruhr's industry became essential. Europe needed German coal, iron, and steel during its reconstruction. By the late 1950s, the German government subsidized Ruhr coal in order to combat imports, which boosted Ruhr production and pollution to new levels. The Ruhr's air quality became a national political issue in 1961 when Willy Brandt, campaigning for the chancellorship, said the skies over the Ruhr must become blue again. Brandt lost, but effective smoke and soot regulation followed in the 1960s, especially after he became vice-chancellor in a coalition government. Tall smokestacks went up, broadcasting the sulfur emissions downwind. This tactic, common in all industrial regions, distributed pollution over wider areas in less concentrated doses. Politically, this often soothed matters and delayed effective emissions reduction. In the Ruhr, it took until the early 1980s and the emergence of a German Green Party before the accumulated evidence of sulfuric acid rain generated the political will to clamp down on emissions. The Ruhr's record of unbridled air pollution prior to the 1960s and considerable improvement in the subsequent 30 years is paralleled in the industrial regions of the United States, Japan, Sweden, and Britain. By and large, the industrial centers of the USSR and Eastern Europe remained impervious to pressures to reduce pollution until the 1990s. Billowing smokestacks carried a totemic aura among Marxists. Heavy industry promised both power for the state and proletarianization of society. Hence iron, steel and coal, and later chemicals, cement, and oil became priorities in the economic plans of the USSR and after 1948 of its East European satellites. Among the many consequences were vast regions of intense air pollution and hence an additional grievance against communist rule. The sulfuric triangle. The triangle bounded by Dresden, Prague, and Krakow sits on rich seams of brown coal, high in sulfur and ash. Early industrialization took advantage of these deposits and of water power from the Tatra and Sudeten mountains. The first blast furnace in Europe opened in Gliwice in 1796, inaugurating a long era of coal, iron, and steel production in what is now Polish Silesia. By 1900, this region supported a considerable industrial establishment, second in Europe only to the Ruhr. Notable air pollution in this region dates from the late 19th century. Czech forests showed the ill effects of a high-sulfur diet from the 1920s. The Depression checked industrial production and pollution, but then war stimulated it. Entirely under German control by late 1939, the region contributed heavily to the Nazi war effort. American bombing in Soviet artillery flattened most of its industry in 1944 to 1945. But its coal remained, and industrial development suited the interests and ideology of the communist parties in charge after 1948 in Czechoslovakia, Poland, and East Germany, and their overlords in Moscow. So heavy industry returned, expanded, and polluted skies as never before. Plant managers and party planners had even less to worry about in the way of resistance to pollution than had the lords of the Ruhr. The communists destroyed the landed interest quickly in Eastern Europe and monopolized information and power so successfully that discordant opinions were rarely voiced in public until the 1980s. Moreover, the economic growth rooted in rapid industrialization improved average living standards, so polluting smokestacks in the sulfuric triangle, as in Jada, Pittsburgh, and the Ruhr. 3. Regional air pollution, the Ruhr and the sulfuric triangle. By the 1970s, pollution attained gargantuan proportions. Northern Bohemia had the most intensive pollution in Europe because of its extraordinary concentration of coal-fired power plants. Coal provided 3/4 of Poland's energy and 2/3 in Czechoslovakia and East Germany. In the 1970s, 2/3 of Poland's sulfur emissions came from Upper Silesia, only 3% of the nation's territory. Polish Silesia also acquired millions of tons of pollutants with the west wind from Czech and German provinces. By one calculation, the intense pollution in Upper Silesia and Krakow in the mid-1970s killed 6 to 7 people per thousand each year. Life expectancy in Upper Silesia was shorter than elsewhere in Poland, genetic mutations and childhood developmental disabilities more common. 10. Whereas the Ruhr after 1970 achieved some measure of control over industrial emissions, air pollution levels in the sulfuric triangle continued to climb, albeit more slowly, in the 1980s. Coal subsidies and fuel inefficiency remained standard. East Germany generated more sulfur dioxide per capita or per unit of GNP than anywhere else in the world. By 1990, Poland's Upper Silesian sulfur emissions were 5 times as great as the Ruhr's. Authorities in Poland initially denied that pollution existed in socialist economies and eventually found it prudent to make environmental information state secrets. Consequently, the citizen pressure, politicization, and media crusades that forced emission reductions in the Ruhr while leaving basic structures of society intact had no parallel east of the Iron Curtain. Since the state shielded polluters so thoroughly in Eastern Europe, citizen outrage at pollution, pent up for decades, was directed at the state itself, not at individual firms. This contributed to the demise of the communist states in the years 1989 to 1991. Even these world-shaking events could not change geology. The brown coal remained and continued to power industry and pollute air in the 1990s. In the former East Germany, the events of 1989 to 1991 led to reunification, investment, technical improvements, and quick changes in energy efficiency and pollution control, much of it achieved through greater use of natural gas. In Polish and Czech lands, changes came more painfully. Czech air pollution levels declined by almost 50% between 1985 and 1994. But improved air quality in both countries often came from plant closings more than from technical improvements. 11. The air pollution experience of the Ruhr and the sulfuric triangle in the 20th century shows the firm devotion of European states to industrial growth, the devotion of Western firms to profit, the fervid commitment of the communist states to outproducing the West, and the low priority that air quality and human health commanded. But it also shows how, after 1970, more politically open societies could change under social pressures, while more restricted and inflexible polities remain choked in the grip of pollution. 12. The air in Japan. In Japan, air pollution reached very high levels by 1970 and then subsided. Both the pollution and its abatement were linked tightly to Japan's politics, international, national, and local. Japan shared many of the same commitments and characteristics that caused so much pollution in the sulfuric triangle and the Ruhr. From the 1870s, it rapidly built dense concentrations of industry. Crowded cities and polluting industries lived cheek by jowl. Until the mid-1960s, the state scarcely regulated the big firms on which its power, especially its geopolitical position, largely rested. In Japan, as in Germany, powerful nationalism translated into determined efforts to industrialize quickly, regardless of social and environmental costs. Japan and Germany can each lay plausible claim to the most polluted air in the 20th century. 13. From the Meiji Restoration until about 1965, Japan was a polluter's paradise. 14. But by 1975, Japan's air pollution problem was under control, and by 1985, Japanese enjoyed cleaner air than almost any other industrial populace in the world. This was a dramatic turnaround, which, like the Ruhr, Pittsburgh, or Cubateo, shows how reversible even intense air pollution can be. Copper mines and smelters, 1885 to 1925. Mining and smelting gave Japan early experience with acute air pollution. The air and water pollution at the Ashio mine provoked tense political struggles in the period 1890 to 1905. The Beshi copper mine, on Shikoku Island, caused pollution problems from the 17th century on. After 1885, the expansion of mining and smelting at Beshi intensified pollution and provoked 40 years of intense complaint and political tussle. To avoid the political problems of Ashio, the government encouraged mine owners to install anti-pollution devices. In 1910, the Minister of Agriculture, responding to agitation by farmers, coerced the proprietors, Sumamoto interests, into restricting Beshi's operations during a 40-day span crucial to the maturation of rice. This practice, following a precedent set in Wilhelmine, Germany, reduced but did not resolve anti-pollution struggles. After 1925, desulfurization equipment and a 48-meter smokestack diffused local pollution and diffused political pressure. The Hitachi copper mine after 1905 followed the same course of increased local pollution and public protest, resolved by a 155-meter stack, tallest in the world, built in 1914, 1915.15. Only a few communities succeeded in restraining air pollution, and usually their success consisted of the dilution and export of offending substances. Meiji Japan's intense commitment to industrialization, militarization, and imperial success legitimated the sacrifice of local and regional communities for the national interest. Its centralized power structure made such sacrifice feasible. A fisherman whose livelihood was destroyed by the Yada steelworks reflected, with the development of the Japanese nation and the development of this region, it is us fishermen who have become the victims. 16 But fishermen did not run Japan. 4. Key locations in Japan's air pollution history. The Hanshin region, 1890 to 1970. The acute air pollution of mines and smelters affected small regions but presaged larger problems. The Hanshin region hosted more heavy industry than anywhere else in Japan except possibly Greater Tokyo. Long a textile center, after 1880 the region bristled with new iron, steel, cement, and chemical plants. Population in Osaka and Kobe doubled in the 1880s to about 620,000 and doubled again by 1900. Victory in the Russo-Japanese War vindicated the Japanese economic strategy and redoubled government commitment. Hanshin's industries spilled out amid residential and farming districts, causing acute social stress. Smoke and sulfur dioxide poured forth from thousands of smokestacks onto millions of people. Hanshin was the equivalent of the Ruhr, an essential industrial zone where national interest justified intense pollution. Osaka began to monitor air pollution in 1912. Its smoke and ash concentrations rivaled those of St. Louis, Cincinnati, London, or Berlin. 17 Osaka was a coal city like London or Pittsburgh. The Japanese called it Smoke City Osaka. As in other coal cities, murmurs of dissent arose against the orthodoxy of industrial development. Nascent political pressure to curb pollution foundered when the demands and opportunities of World War I arose. Japan played only a small role in that conflict, but when it ended, managed to acquire German colonies in the Pacific and some German concessions in China. The chaos in the Russian Far East after the Bolshevik Revolution gave Japan another opportunity to flex its imperial muscles, for which it needed more steel, ships, and weapons. Hanshin boomed. Its air pollution got worse in the 1920s, despite a 1925 law that required smoke prevention equipment on urban buildings. Administration and regulation could not keep pace with urban growth. Osaka doubled in population in the 1920s, while expanding territorially. The whole Hanshin region was humming with the rapid growth of Japan's economy. Dozens of air pollution disputes led Osaka Prefecture to organize smoke prevention efforts, culminating in a 1932 law designed to increase combustion efficiency and reduce smoke. But the city of Osaka alone had 35,000 smokestacks in 1932, and only 3 smoke inspectors. With the inauguration of Japan's imperial adventure in China, more metallurgical and chemical plants were built in Hanshin, and smoke levels doubled. Airplanes crashed on account of reduced visibility. But no pollution restrictions carried weight, as Japan's overriding priority became war production. Smoke, ash, dust, and sulfur bathed the region until American air power pounded Hanshin's industry to rubble in 1944-1945. After 1945, Hanshin stagnated until the Korean War, when, as in the Ruhr, American geopolitical anxieties required the resurrection of industry recently destroyed by American bombers. Dustfall in Osaka, in 1945 only a quarter of 1935 levels, by 1955 surpassed pre-war heights. 18 automobiles, a small factor in Hanshin air pollution in the 1930s, added to the dark clouds from the 1950s, especially after 1970, when Osaka, Kobe, Kyoto had nearly fused into a single sprawling motorized conurbation. Smokestack and tailpipe pollution flourished until 1970, causing widespread health problems for a population approaching 10 million. Hanshin, like the Ruhr or Norilsk, was a place where polluting enterprises were protected in the national interest, a pollution reserve. The Hanshin region was only one of several places severely polluted during Japan's economic miracle. Ube, a cement, chemicals, and coal center in the far southwest of Japan, suffered notoriously foul air. The Yada Steelworks, opened in 1901, by 1961 was blowing 27 tons of soot and dust out of its smokestacks every day and presumably contributed to the unusually high rates of respiratory disease observed in surrounding precincts. And Tokyo, where the air was polluted from the late 19th century, if not so badly as Osaka's, acquired an acute photochemical smog problem by 1970 due to growing auto use. 19. The Japanese economic miracle, like the German Wirtschaftswunder, came at a heavy air pollution price. But by the late 1960s the air all over Japan was beginning to clear. The Japanese environmental miracle, 1965 to 1985. Several convergent forces allowed Japan to change environmental course without derailing the engine of economic growth. The most important were a system of local government that responded to local concerns, an energy shift away from coal, widespread prosperity that encouraged citizens to question the necessity of pollution, and the extraordinary rate of capital accumulation that allowed industry to spend on pollution control when obliged to. Bube took effective action first. In the early 1950s, an unusual coalition of academics, industrialists, and local bureaucrats formed. Epidemiologists from the local university's medical school demonstrated the health consequences of Ube's foul air. Kenichi Nakayasu, a leading industrialist who had visited Pittsburgh before World War II, went there again in 1954 and saw and smelled the difference. He convinced his peers that Ube could clear its air. Bureaucrats composed new regulations on emissions, chiefly of dust and smoke, and by 1961 Ube's air became a transparent shadow of its former self. Elite-driven reform worked. Its regulations became the basis for national law in 1962 that controlled, with indifferent success, smoke and soot. Compliance with the 1962 smoke and soot law did not come naturally to most Japanese industrialists, but citizens and the state gave them a nudge. The 1962 law did nothing to curtail emissions of sulfur dioxide or heavy metals. Air pollution levels in Japan by the late 1960s were worse than ever before. Citizen action drove the next phase of reform. In 1967, asthma sufferers in Yokkaichi sued the giant petrochemical complex operating there since 1959. In 1972 they won large damages amid great publicity. The Mie prefecture soon imposed tight sulfur emission standards. At the Yada Steelworks, women pressured authorities into pollution abatement. Several prefectures cancelled planned industrial complexes in the late 1960s, prompted by pollution and health concerns, an extreme departure from the previous mentality and practice in Japan. By the late 1960s, new plants had to have pollution control technology to get local approval. Japan's limited supply of suitable terrain put local authorities in good bargaining positions vis-a-vis industrialists, allowing them to impose conditions that would not fly in countries with large expanses of flat ground. Indeed, the industrialist who valued good community relations found it prudent to police factory emissions more hawkishly than the law required. But the law was usually not far behind. Pollution control entered the main stage of national politics by 1965, well-publicized lawsuits continued, and people and prefectural authorities learned more and more about pollution and pollution control. A particularly bad smog episode in Tokyo in the summer of 1970 helped focus the attention of the national government, which later in that year passed a spate of anti-pollution laws and created a new agency to monitor environmental affairs. Standards grew tighter, industrialists invested in new anti-pollution technology, and Japan's skies got much, much cleaner. By 1975, Japanese businessmen were trying to sell pollution control technology in Cubateo. Japan even achieved quick control over car emissions. Tokyo's car fleet quadrupled to 2 million from 1960 to 1970. When the head of the American EPA appeared before Congress to sell the U.S. Clean Air Act of 1970, he used Tokyo, where traffic policemen wore masks to filter the air, as an example of how bad things could get. Tokyo brewed world-class smog and lived in a permanent dusk. 20MIDI, the all-powerful Ministry of International Trade and Industry, reacted to public outrage by creating emission standards for the auto industry, following those the United States implemented in 1970. In both countries, the car companies claimed the standards could not be met. The American companies sued the EPA. Japanese companies complained loudly but worked vigorously to meet MIDI and EPA standards. Some companies met both, years before the law required it, which helped them surge into the American car market in the 1970s. By 1978, new Japanese cars emitted only about 10% as much pollution as had new 1968 models. 21 The Japanese aversion to old and used cars helped modernize the fleet rapidly and drastically reduce tailpipe emissions. By the early 1990s, Japanese cities such as Osaka and Tokyo, and Japanese industrial districts such as Hanshin, suffered far less air pollution than they had in the 1960s or the 1930s. 22 Behind this remarkable turnaround stood some favorable conditions. Japan's struggle with smoke and soot ended well in large part because coal gave way to oil and other energy sources. Anti-pollution technology made rapid progress, assisted by Japan's extraordinary capacity to import, modify, and assimilate useful technologies and laws. Japan, which had assiduously studied Western legal codes in the early Meiji years, a century later adapted pollution control law from Germany, Britain, and the United States. Japanese society in the boom years also saved at uniquely high rates, allowing prodigious capital investment. A proportion of this could go to pollution control, occasionally above and beyond legal requirements. It also went to energy efficiency, gospel in Japan after 1973. MIDI funded appropriate research, and by 1983 mining and manufacturing used one-third less energy than in 1973. Most importantly perhaps, after the 1947 Constitution, Japanese municipal and prefectural officials became very responsive to citizen concerns, disciplined more by local elections than by Tokyo. This tempered the tendency to sacrifice local environments for the greater glory and progress of the nation, a strong tendency after 1868. The Japanese environmental miracle, like the economic one, derived from a mix of factors, several of which were distinctly Japanese. 23. Acid rain. Sometimes regional pollution extended across international borders. The major issue in transboundary air pollution was acid rain, derived from sulfur and nitrogen oxides. Unlike most pollutants, they last long enough in the atmosphere to travel thousands of kilometers. Fossil fuel combustion in each of the great industrial heartlands of the 20th century generated huge sulfur emissions, the main ingredient in 20th century acid rain. 24 Japan's emissions tended to wash out over the Pacific. The emissions of other countries created frictions between neighbors. The most important such cases involved acid rain in Northern Europe, Eastern North America, and East Asia. In Europe, detectable international transport of air pollution annoyed sensitive observers from at least the 1860s. The Norwegian playwright Henrik Ibsen complained about airborne British grime crossing the North Sea. 25 But attention focused on the issue only in the 1960s, when Scandinavian scientists showed that acid rain derived from British coal combustion had strongly affected the rivers and lakes of southern Sweden and Norway. Further monitoring and research revealed enormous international flows of air pollution, mainly sulfur dioxide, broadly moving from west to east with the prevailing winds across Europe. 26 Iceland and Portugal received almost no imported pollution, Scandinavia and Poland plenty. The tall smokestacks required to avoid acute local pollution problems naturally increased transboundary pollution. Acidification affected soils and waters across Europe, but especially the broad belt from Birmingham to Bratislava, where coal and car use was concentrated. Even rural areas far from any industry showed ill effects, mainly damage to trees, lakes, and streams. The thresholds beyond which acid buildup causes biotic problems are quite variable. The limestone soils of Greece can neutralize 10 times as much acid as the sensitive soils of Scandinavia. Europe's industrial growth, energy use, and motorization from 1950 to 1980 poured enormous quantities of sulfur and nitrogen into the air, creating acid rain as never before. Addressing problems of this scale and complexity required international cooperation. In 1985 and 1994, most European countries signed protocols requiring sulfur emission reductions, the second of which recognized the importance of varying critical loads. In fact, European sulfur emissions dropped 15%, driven at first by energy efficiency stimulated by the fuel prices hikes in the 1970s. 27 Controlling nitrogen oxides means controlling car emissions, on which Europe made less progress, despite an international protocol in 1988. Long-range pollution transport, and acid rain in particular, continued to burden Europe's ecosystems into the 1990s. The politics of air pollution control suffered from the fact that Europe comprised so. Yet similar problems plagued Eastern North America, where only 2 countries were involved. There, as in Scandinavia, lime-poor thin soils and waters proved vulnerable to acidification. The industrial belt of the Great Lakes and Ohio River Valley spewed forth abundant acidic emissions. In the 1970s and early 1980s, rain here typically was more acid than root beer, and occasionally more so than Diet Coke. 29 The ecological consequences, first detected in the 1950s, soon became conspicuous in the lakes and rivers of Quebec, the Maritime Provinces, New England, and New York. In the 1980s, half of Canada's sulfur deposition came from the United States, which shaped the politics of North American acidification. But the political situation was complicated by the position of northeastern states on the receiving end of Midwestern sulfur emissions. Ontario's emissions wafted over Quebec and the Maritimes, as well as over the northeast United States. After 1975, the USA and Canada reduced sulfur emissions by 15 to 25%, roughly as much as Europe achieved after 1980. The extraordinary industrialization of East Asia in the 1980s generated a new arena of transboundary air pollution. Here Japan found itself showered by acid rain from Korea and China. By 1996, in some parts of Japan, half of all acid deposition came from Chinese sources. Japan, like Canada and Norway, became a member of the Unhappy Downwind Club and began to sponsor more research and international dialogue on acidification. China, whose acidic fallout wafted across the Philippines, Taiwan, and Korea as well as Japan, joined the United States and the United Kingdom as net pollution exporters, generally serving as brakemen on international cooperation. In the 1990s, transboundary pollution in East Asia remained small in quantity and political weight by European standards, but was growing fast. 30. The number and size of regions affected by transboundary pollution grew exponentially in the 20th century. Although sharp impacts remained confined to Europe, East Asia, and Eastern North America, faint impacts became hemispheric in proportion, and less faint. 31 In 1995, a space shuttle monitoring device noticed a sulfur plume wafting across the Atlantic from North America to Europe. 32 The atmospheric archives in Greenland ice caps show that sulfur and nitrogen emissions in the northern hemisphere as a whole circulate into the polar region. Greenland ice shows 2 surges in sulfur deposition, a modest one around 1875 to 1910 and a strong one around 1945 to 1975. Since 1950, the ice records a sharp jump in nitrogen deposition. Taking all acidifying compounds together, satellite monitoring in 1994 showed a giant region stretching from Britain to Central Asia in which highly acid rain regularly fell. 33 In the southern hemisphere, by comparison, acid rain and other air pollution remained local in scale with few exceptions. Although after 1985 European countries achieved agreements on emissions controls, in most cases international air pollution flows proved harder to limit than local, urban pollution. Multiple centers of political power were involved, not merely nation-states, but provinces within countries, which sometimes worked at cross-purposes with national governments. This hampered coordination. Furthermore, distrustful neighbors, like Japan and China, found it difficult to cooperate. The actions that generate most long-range pollutants, coal combustion and driving, are difficult for most economies to sacrifice. For all these reasons, political will was rarely equal to the task of reduction in transboundary pollution. Further consequences of air pollution. Pervasive air pollution, on scales never previously reached, predictably enough had numerous consequences, few of them welcome. From the anthropocentric point of view, the most important ones involved human health. Air pollution and human health. The health consequences of air pollution in the 20th century were gargantuan, although hard to measure precisely. By 1992, on one World Bank estimate, particulates alone in the world's cities killed 300,000 to 700,000 people a year. 34 in 1996, the Harvard School of Public Health put this figure at 568,000. 35 in 1997, the WHO estimated that all air pollution killed 400,000 people worldwide annually. 36 taking the lower figure, and assuming that at-risk urban populations quadrupled since 1950, that the increasing lethality of air pollution in China, the Third World, and the Soviet bloc offset the air quality improvements in Japan, Western Europe, and the United States. I reckon that air pollution killed about 20 million to 30 million people from 1950 to 1997. For the century as a whole the figure would be only a bit larger, because urban populations were smaller, although in the Western world air pollution was worse. All told, a guesstimate for air pollution's 20th century toll would be 25 million to 40 million, roughly the same as the combined casualties of World Wars I and II, and similar to the global death toll from the 1918-1919 influenza pandemic. The 20th century's worst encounter with infectious disease. That guesstimated, it must be said that death from air pollution and death from war, while ultimately perhaps equivalent, are from the social and economic point of view, quite different matters. In the 20th century, war killed people mainly in the prime of life, air pollution killed the sick, the elderly, and the very young. If one esteems all individuals equally, then the toll from air pollution may be reckoned as equivalent to the toll from the world wars. But if one considers instead that the elderly have already made what contributions to society they are likely to make, and that the very young, having had little invested in them, are very easily replaced, the calculus changes to 37. In the United States after the late 1970s, air pollution killed roughly 30,000 to 60,000 people per year, about 2 to 3% of all deaths. 38 among causes of death in the United States, it ranked with automobile accidents, slightly ahead of guns, far behind tobacco. However, it killed mostly elderly people, those most prone to respiratory infection and cancers, whereas cars killed people of all ages and guns mostly the young. So in terms of total years of life lost, air pollution significance in the United States was much less than auto accidents or guns. In addition to killing tens of millions in the 20th century, air pollution provoked or aggravated chronic illness among many more, perhaps hundreds of millions. Particulates, especially tiny ones, promote respiratory infections and probably cancer. Lead damages nervous systems and inhibits mental development. Some epidemiologists think the absorption of ambient lead by American children in the years 1950 to 1980 reduced average IQ scores. In Poland and Bangkok, the health impacts of lead exposure were more severe. 39 further health problems arose from sulfur dioxide, which causes respiratory problems, especially for people who already have bronchitis. In Japan, where a pollution compensation law in effect from 1973 to 1988 occasioned careful studies, 90,000 people qualified for payments on account of health problems attributed to air pollution, mainly sulfur dioxide, in the vicinity of the Yokkaichi petrochemical complex. Disentangling the impact of air pollution on health from other causes of death and disease is no easy matter. Indoor air pollution, particularly in the poorer countries where biomass and coal served as domestic fuels, produced the same ailments and probably killed millions more. That said, it is well to remember that polluted water caused far more death and disease than did polluted air in the 20th century. 40. Air pollution, plants, and animals. The ecological consequences of 20th century air pollution were at least as difficult to assess as the human health impacts. Air pollution supplemented natural selection with unnatural selection, favoring some creatures and harming others. The sharpest impacts occurred in the extreme cases, such as Cubateo or around Sudbury and Norilsk, where pollution created moonscapes. The broadest impacts derived from regional pollution, notably acid rain. In between were the coal cities, where air pollution affected the biota noticeably but not devastatingly. The great coal cities, with their smoke and acid rain, stunted and killed local vegetation, as did the great smelters. Conifers disappeared from coal cities because of their sensitivity to acid. Poplars and willows did better. Several varieties of sycamore became favorites of urban planners in the late 19th and early 20th centuries because of their stout resistance to air pollution. The legacy is visible in parks and along avenues from London to Tashkent. After 1970, in Britain and Japan at least, acid-sensitive trees have made a slow comeback. 41. Coal cities took a small toll on animal life too. Lions in the London Zoo used to die routinely of bronchitis, birds from necrosis of the lung, many other creatures from anthracosis and silicosis, all caused by particulates in the lungs. Prize beasts at London's Islington cattle show suffocated during the notorious fog of December 1873. The smoke of coal cities created a new selective pressure in evolution, most visible in changing moth populations in London and the English Midlands. In the course of the 19th and early 20th centuries, darker moths came to predominate, presumably because they had better camouflage than whiter moths. But late in the 20th century, when smoke abated, whiter moths recovered their numbers and the dark ones suffered. 42. By far the greatest ecological impacts of air pollution derived from regional pollution. Sulfur emissions damaged trees from the late 19th century. By the late 20th, acid rain and ozone damaged broad swaths of forest. In Scandinavia and Central Europe, millions of trees after about 1970 showed signs of decline, growth slowed, leaf density dropped, and many died. Conifers and oaks suffered most. By the 1990s, about a quarter of Europe's trees showed damage. 43. In the northern Czech Republic, whole forests died and acid deposition made soils too toxic for trees. The world's other acid rain centers, Eastern North America and East Asia, suffered less. While most students of Waldsterben, as it is called in German lands, attribute this phenomenon to air pollution, chiefly acidic emissions and ozone, rival explanations existed. 44. Less visibly but more costly perhaps, air pollution also damaged crops. 45. Acid rain unambiguously affected aquatic life. Where underlying rock did not neutralize excess acid, lakes and rivers in the course of the 20th century often became inhospitable to crustaceans, snails, mollusks, frogs, and the more acid-sensitive fish such as salmon and trout. In Europe and Eastern North America, hundreds of thousands of rivers and lakes lost all or part of their aquatic life on account of acid rain after 1960. In Norway, recipient of a goodly share of Britain's sulfur emissions, ill effects date from at least 1920. Air pollution and cultural monuments. The acidic brew emitted by smokestacks and tailpipes corrode stone, especially limestone and marble. Some of the great cultural monuments of the world consequently decayed at heightened rates in the 20th century. Where susceptible stone and heavy pollution existed in close proximity, as in many cities of Europe, the cultural loss was most pronounced. Acidic London fogs gnawed away the stone facing of St. Paul's Cathedral at a rate of about 8 mm per century. Athenian car exhausts damaged the ancient marble on the Acropolis more seriously in 25 years than did all the weathering of the previous 2,400 years. The magnificent horses of St. Mark, much tossed by the tides of history, finally succumbed to air pollution in 1974. Venetian authorities hid them away and replaced them with fiberglass imitations atop the cathedral. Michelangelo's David could not be trusted to Florentine air, a replica stands in his place at the Piazza della Signoria. Less exalted monuments and buildings suffered too. In the early 1990s, it cost Europe about $9 billion per year to replace corroded stone. With effective pollution control in parts of Europe, corrosion of building stones slowed somewhat after 1970 but did not cease. 46. Air pollution's cultural corrosion, while fastest in Europe, emerged elsewhere after 1980. Refineries at Agra emitted sulfur dioxide that ate away at India's incomparable Taj Mahal. Mayan limestone monuments at Tikal, in Guatemala, showed the ill effects of Mexican oil combustion 100 kilometers away. The Sphinx, the pyramids, and other great pharaonic monuments of Giza, survivors of 40 centuries of intermittent sandblasting by the Sahara, decayed visibly under the impact of Cairo's pollution. Coal dust damaged the 5th century AD sandstone statuary in China's Yungang grottos, which house 50,000 statues, including Buddhas as big as 3 or 4 elephants. 47 Those now living will be the last generation to see these monuments and artworks in anything like their original forms. Air pollution, economics, and politics. Air pollution in the 20th century had significant but mostly unmeasurable economic and political effects. The forests, crops, buildings, bridges, monuments, machinery, and human health damaged or destroyed cost untold billions. The World Bank in 1997 estimated that China's air pollution cost the country 8% of its GDP. The figure would be smaller in other countries. 48 Until 1970 or so, these damages, if recognized at all, were widely considered an acceptable cost of doing industrial business. After 1970, events showed this need not be the case, and that pollution control could be profitable in its own right. After 1980, air pollution control grew rapidly and became a multi-billion-dollar industry. The shift around 1970 reflected one of the important popular political mobilizations of the 20th century. It centered on the historic heartlands of pollution, North America, Europe, and Japan, but emerged elsewhere too, notably in India. This was all part of the general environmental movement. Beyond air pollution's role in catalyzing modern environmental politics, it played a small role in international affairs as well. Long-distance transport of air pollution provoked frictions between close allies, such as the United States and Canada, Britain and Norway, and the former East Germany and Poland. It exacerbated tensions between edgy neighbors such as China and Japan, and Norway and Russia. However, air pollution's role in international politics was not all dark. Numerous international agreements, protocols, accords, and treaties arose to address air pollution problems, beginning with small-scale bilateral agreements, but after 1975 involving regional and even near-global accords. The complexity of the issues involved required the participation of scientists, which perhaps eased negotiations. 49. Climate change and stratospheric ozone. In the 20th century, human activities increased the presence of greenhouse gases in the atmosphere and reduced the concentration of ozone in the stratosphere. These two changes have enormous potential consequences for the history of the 21st century. In the 20th century, their consequences were mild. But because their portent is so significant for human affairs, and because the origins of climate change. The major greenhouse gases are carbon dioxide, methane, and ozone. 51 While climate is governed by many factors, among the crucial ones is the composition of the atmosphere. Without any greenhouse gases, our planet would be a chilly place, more like Mars, where temperature averages are around -23 degrees Celsius, like Earth's Arctic winters. With more greenhouse gases, Earth would resemble Venus, where temperatures are well above the boiling point. For life adapted to Earth, changes in greenhouse gases are serious business. For the 1,000 years before 1800, carbon dioxide levels in the atmosphere varied around 270 to 290 parts per million. Around 1800 an accelerating buildup began, reaching about 295 ppm by 1900, 310 to 315 ppm by 1950, and about 360 ppm in 1995. Two trends drove this buildup: fossil fuel combustion, which accounted for about 3/4 of the addition, and deforestation, which accounted for almost all the rest. Meanwhile, methane, which like carbon dioxide is present naturally in the atmosphere, increased from about 700 to about 1,720 parts per billion. The main sources of methane buildup were agriculture, especially irrigated rice, livestock, garbage decomposition, coal mining, and fossil fuel use. These minute but momentous changes in the atmosphere, in concert with some even tinier ones involving other greenhouse gases, made the atmosphere more efficient at trapping heat from the sun. At the same time, human actions injected lots of dust and soot into the atmosphere, which slightly lowered the amount of solar energy reaching the Earth's surface. The net effect, since 1800 or so, was about 2 more watts per square meter of solar energy delivered to the Earth's surface. This probably accounts for the modest warming the Earth experienced in the 20th century. 52. The Earth has warmed up recently, although no one knows for certain if human actions are the cause. Between 1890 and 1990, average surface temperatures increased by 0.3 degrees to 0.6 degrees Celsius. That happened in two surges, between 1910 and 1940, and then after 1975. From 1940 to 1975, average temperatures actually declined slightly. But 9 of the 10 hottest years on record occurred between 1987 and 1997, and the 1990s promised to be the hottest decade since the 14th century. 53 changes of this magnitude and rapidity are well within the natural range of variation, although rare within the last 2 million years, probably non-existent within the last 10,000 years, and definitely absent within the last 600 years. 54. Some places warmed more than others, and some have cooled. The greatest warming took place in the northern hemisphere's higher latitudes, above 40 degrees, north of Philadelphia, Madrid, and Beijing. Here, for example, the growing season lengthened by more than a week between the late 1980s and 1997.55. Antarctica too warmed up a lot, and its ice melted faster than before. 56. Whether or not the climate grew more unstable, bringing more droughts, hurricanes, heat waves, floods, El Niño events, and the like, remained uncertain. The Intergovernmental Panel on Climate Change, the United Nations' authority on the issue, decided in 1995 that no conclusion was yet possible. By the late 1980s, insurance companies, careful students of the probabilities of extreme weather, suspected climate had indeed become more unstable. 57. The consequences of the warming of the 20th century remained small. Some creatures shifted their habitat range to avoid the heat. Some glaciers and ice caps shrank, and sea level rose by 10 to 25 centimeters, up to one's ankle or mid-calf. Quite plausibly, but quite unprovably, this rise extended the damage done by storm surges to the coasts of Bangladesh and other low-lying countries. Malarial. Mosquitoes expanded their range, particularly into higher elevations in tropical Africa, raising the death toll from malaria in places such as Rwanda. In the larger picture of 20th century history, perhaps none of this amounts to much. The much greater warming forecast for the 21st century and beyond, however, will be quite another thing. In the late 1990s, most climate modelers expected that in the 21st century average temperatures would rise perhaps 1 degree to 5 degrees Celsius. 58. If their models were to prove correct, this warming implies vast changes in evaporation and precipitation, a more vigorous hydrological cycle making for both more droughts and more floods. The consequences for agriculture, while difficult to predict, would be sharp. 59. Human health would suffer from the expanded range of tropical diseases and their vectors. Species extinctions would accelerate. Coping with warming on this scale, assuming it happens, will be a major chapter in the history of the next century. For some low-lying island nations, such as the Maldives, it could also be the final chapter. 60. Ozone and chlorofluorocarbons. The history of stratospheric ozone depletion also commands attention more for its future prospects than its past importance. Up in the stratosphere, sunlight and oxygen react to form ozone, which absorbs 99% of the ultraviolet radiation. 61. Entering the atmosphere. Before there was oxygen, there was no ozone layer, and life on Earth had to stay underwater. This indispensable sunscreen, consisting of ozone molecules circulating in the vastness of the stratosphere at concentrations of only a few parts per billion, took eons to form. This thin shield then protected life on Earth admirably for about a billion years. But in 1931, Thomas Midgley invented Freon, the first of the chlorofluorocarbons, which proved useful in refrigerants, solvents, and spray propellants, among other things. Freon replaced dangerously flammable and toxic gases previously used in refrigeration and made air conditioning practical. The virtue of CFCs and other like gases is that they are very stable and react with almost nothing until they drift into the stratosphere, where direct UV radiation breaks them up, releasing agents that in turn rupture ozone molecules. Midgley, the same research chemist who figured out that lead would enhance engine performance, had more impact on the atmosphere than any other single organism in Earth history. He was born in Beaver Falls, Pennsylvania, in 1889 into a family of inventors. He grew up in Dayton and Columbus, graduated from Cornell University, and went to work as a chemical engineer. During World War I, he worked on aerial torpedoes and synthetic airplane fuel. In 1921, while working for General Motors Research Corporation, he found that tetraethyl lead reduced engine knocking, and in 1923 his employers marketed ethyl gasoline for the first time. Midgley's work made high-compression auto and aircraft engines possible. At the request of General Motors' Frigidaire division, Midgley then tackled problems of refrigeration. In front of a large audience at the 1930 meeting of the American Chemical Society, he demonstrated the non-toxic and non-flammable properties of Freon by inhaling a lungful and then slowly exhaling over a lighted candle, which the Freon extinguished. Holder of over 100 patents, winner of all the major prizes in chemistry in the United States, Midgley was president of the American Chemical Society at the time of his peculiar death. He had contracted polio in 1940 and designed a system of ropes and pulleys to help him in and out of bed. In 1944 he died of strangulation, suspended above his bed, entangled in his network of ropes, killed by the combination of bad luck and his own ingenuity. Midgley was the Fritz Haber of the atmosphere. 62. Only after the Depression and World War II did Midgley's invention catch on quickly. CFC releases remained small in the 1930s and 1940s, reaching perhaps 20,000 tons annually by 1950. But by 1970, emissions reached about 750,000 tons, and an unnoticed assault on the ozone layer was in full career. In 1974, scientists Sherwood Rowland and Mario Molina suggested the theoretical possibility that halocarbons might thin the ozone layer. In 1985, J. C. Farman's observations confirmed that over Antarctica this had indeed happened. 63 subsequent measurements showed mini-holes over Chile and Australia. Meanwhile, the ozone shield over the northern hemisphere thinned slightly, over the tropics not at all. 64. The initial discoveries prompted an unusually quick political reaction because the prospects of enhanced UVB radiation were more than worrisome. It kills phytoplankton, the basis of oceanic food chains. It affects photosynthesis in green plants. In humans, it causes cataracts and other eye ailments, suppresses immune system response, and in susceptible people causes skin cancer. The United States, Canada, and Scandinavian countries banned CFCs in aerosol sprays in the late 1970s. This had little overall effect. Global CFC releases continued to climb. In response to Farman's findings, the United Nations Environment Programme organized the 1985 Vienna Convention on Ozone Depletion. It led to the 1987 Montreal Protocol, the 1990, 1992, and 1995 amendments, altogether an extraordinary international response to an extraordinary problem. These agreements sharply curtailed production of CFCs. Chemical manufacturers, who had for years argued against the theory that CFCs might damage the ozone layer, initially complained about the protocol and amendments but quickly found substitutes. Some chemists who had used CFCs as solvents found that water or lemon juice worked just as well. After 1988, the rate of CFC releases dropped. The big users lowered CFC use by 75 to 100%. China and India used more than before, but worldwide CFC use declined roughly 80%. That was the good news. Unfortunately, because CFCs are so stable, they last a long time in the atmosphere, and some of those released before the Montreal Protocol will still be destroying ozone in 2087. Hence, the ozone layer will continue to thin for a decade or two at least, before slowly beginning to beef up again. The ultraviolet century in human history should prove to span from roughly 1970 to 2070. 65. It is fortunate for the biosphere, and especially for fair-skinned people and phytoplankton, that CFCs did not become commercially viable 10 or 50 years before they did, that the science of Molina, Rowland, and Farman came no later than it did. And that UNEP already existed to take a leading role in brokering international agreements. In the first 25 years of the ultraviolet century, perhaps 1 to 2 million excess cases of skin cancer derived from stratospheric ozone loss. That translated into about 10,000 to 20,000 early deaths, mainly among fair-skinned people in sunny lands such as Australia. The toll, to date 66, was far smaller than that of respiratory ailments brought on by air pollution. No one knows the full effect of excess UV radiation on immune response, so the real impacts of CFC's erosion of the ozone layer on human health remain entirely unclear. But stratospheric ozone depletion, another combination of bad luck and Midgley's ingenuity, will surely kill many thousands more before the close of the ultraviolet century. 67. While climate change and ozone depletion had only modest effects by the end of the 20th century, their futures were substantially set, although in ways no one can know with precision. Particulates are washed out of the air by rain, and most of the pollutants responsible for local and regional air pollution are similarly removed quickly by natural processes. Hence, local and regional air pollution is easily and quickly reversible, provided one stops adding new pollutants. The global scale issues are different. Were we to stop injecting ozone-rupturing chemicals into the air tomorrow, we would still need about a century before we enjoyed a healthy ozone layer again. With climate change, the turnaround time is longer still. Most of the carbon dioxide added to the atmosphere in the 20th century will remain there for centuries. Carbon dioxide is not rinsed out of the air like soot, rather, it is very slowly absorbed by the oceans and by living things, at rates that cannot be significantly accelerated. Its impacts, great or small, cannot be reversed quickly. So the combustion history of the 20th century has already partly determined conditions in the next several centuries to come. Space pollution. The scale of atmospheric pollution in the 20th century ballooned from local to global, indeed, a little beyond global. Since the Soviet launch of Sputnik in 1957, the great powers have strewn near space with several thousand satellites, rocket boosters, and miscellaneous space junk orbiting at speeds up to 30,000 kilometers per hour. At such velocities, even paint flakes, of which there are millions zooming around, can damage satellites or spacesuits. Astronauts on spacewalks try to stay in the shadow of their spaceships lest they blunder into the path of a rogue rivet. As yet, there are no regulations. Authorities tend to take the view that it is too expensive to do anything, and anyway space is so big that there's room for space junk. Any industrialist would have said the same of the atmosphere 150 years ago. 68. Conclusion. The quantities and consequences of 20th century air pollution were vast. So were the changes in its scale and character. Taken together, our alterations of the atmosphere amount to several simultaneous, inadvertent, and uncontrolled experiments. One of these experiments, urban air pollution, dates from earlier times, but reached levels in the 20th century sufficient to kill many millions of people through respiratory disease. Another, acidification, altered regional ecologies widely in the northern hemisphere. A third, carbon dioxide loading, probably warmed the globe slightly and might yet warm it far more. A fourth, CFC emissions, frayed the ozone layer that makes terrestrial life possible. All of these changes to the atmosphere were accidental effects of industrialization. The main driving force was fossil fuel use, but new technologies played a substantial role too. Behind this industrialization lay the attractions of higher living standards, or at least more consumption, for masses of people, of profit for hundreds of firms engaged in mining, metallurgy, electric power generation, and other polluting enterprises, and of political power for states, bureaucracies, and politicians. Geopolitical anxiety or ambition in particular helped spur Germany, Japan, Russia, China, Brazil, and other polities to industrialize as quickly as possible, almost regardless of consequences. Via air pollution, as well as via violence, the lives and health of millions were sacrificed on multiple altars of national interest. The reductions of air pollution that took place from the 1940s onward were remarkable political events. They required alliances among medical researchers, engineers, citizen activists, legislators, and bureaucrats. In smoke abatement, at least in the United States, the United Kingdom, and Japan, women played a conspicuous role. In the international agreements on acid rain and ozone after 1975, ministers, heads of state, and major corporations took part. Almost all air pollution, except for the global-level problems, proved quickly reversible when addressed at the source. In most of the world and on most issues, the political response to air pollution remained inadequate, in the sense that pollution was worse in the 1990s than in prior decades. But considering the inertia that governs the thinking and politics of most societies, the social and political response to changes in the atmosphere is extraordinary. Sometimes, as Samuel Johnson noted in another context, it is less remarkable that something is done badly than that it is done at all. Chapter 5. The Hydrosphere, the History of Water Use and Water Pollution. Water is good, it benefits all things, and does not compete with them. It dwells in lowly places that all disdain. Lao Tzu. People need water just as surely as they need oxygen from the atmosphere and food grown in the soil. For most of human history, we needed water only to drink. But in the last few thousand years we have relied on it to irrigate our crops, carry off our wastes, wash our bodies and our possessions, and more recently to power our mills and machines. Individuals and societies expended great effort to ensure reliable supplies of water, especially in the dry belt from Morocco to Central Asia. With the modern currents of industrialization, high energy use, and urbanization, societies acquired greater power with which to move and control water. But at the same time, they came to use more, waste more, and pollute more water more thoroughly. The health, wealth, and security of any and all societies depended upon getting sufficient supplies of sufficiently clean water to the right places at the right times, without doing too much damage in the process. Ordinary efforts to achieve wealth and security often complicated this task by polluting water. Success guaranteed nothing, health, wealth, and security required many other things besides adequate water. But failure guaranteed ill health and a weakened economy. Water management, although not always seen as such, was a crucial technical and political challenge. Water basics. Earth is the water planet, the only place in our solar system where water exists as liquid. Water, water everywhere, nor any drop to drink, wrote Coleridge in the Rime of the Ancient Mariner, which could serve as a first approximation of the Earth's condition. Of the hydrosphere's 1.4 billion cubic kilometers, more than 97% is salt water in the oceans. Happily for us, the solar desalination and purification machine pumps up about 500,000 cubic kilometers every year, which falls back to Earth as rain and snow. This is the source of all the world's stock of fresh water. Most of that is currently locked up in ice caps and glaciers, almost all of it in Antarctica. Almost all the remainder lies underground in aquifers, mostly at inaccessible depths. Only about 0.25% of the world's fresh water is in lakes and rivers, where it is most easily accessible. Of this, about a quarter is in Lake Baikal in Siberia. Small amounts of fresh water are in the atmosphere, in permafrost, and in living things. The world's renewable flow of fresh water is somewhat less than its total freshwater stock. Continents get more in rain than they surrender in evaporation, and the difference is the world's stream flow. 2/3 of this runs off in floods, so about 14,000 cubic kilometers per year are available for routine use. This comes to more than 2,000 cubic meters per person annually, which is plenty. But it is spread unevenly around the world. 20 or 30 countries, mostly in Africa and Southwestern Asia, have less than half this figure and are, by the conventional measures of hydrologists, short of water. South America has 10 times as much per person as Asia, and 5 times as much as Africa. The flow is also unevenly distributed throughout the year, so many places have either too much or too little water at any given time. In Cherrapunji, the second rainiest place in the world, the summer months bring about 9 meters of rain. For about 6 months every year, water supply is sufficient, indeed excessive. But for the remaining 6 months, it often is not. The inconvenient distribution of fresh water, coupled with the expense of transporting it over long distances, has made water supply a major constraint on human affairs. Many societies have invested heavily in efforts to ease this constraint. World water use and supply. In the history of water use, some things change, but one thing stays the same. In modern times, as in the past, we have used water mainly for irrigation. Most of our enduring societies and empires were based on the control of water, particularly river water. Egyptian, Mesopotamian, Indic, and Chinese civilizations all rested on irrigation, river transport, and use of river water to dilute and carry off noxious wastes. Skilled water management also underpinned Andean and Mesoamerican civilizations. We have used water for irrigation for 9,000 years and to power mills for 2,000. Now we also need it for industrial purposes, such as hydroelectric power generation, and for cooling and cleaning countless machines. And of course we continue to use water for drinking and for diluting wastes. Following hydrologists, I will divide water use into 3 main categories: irrigation, industrial, and municipal. The clearest thing about the history of water is that people use a lot more now than they used to. In 1700, when the world had about 700 million people, total freshwater use amounted to perhaps 110 cubic kilometers, 90% of which went for irrigation, almost all in Asia. Table 5.1 sketches the quantitative history of water use since 1700. If these figures are accurate, total freshwater use in 1990 was about 40 times greater than in 1700. In the 20th century alone, water use spurted upward 9-fold. Most of the increase probably derived from population growth, which in the same years was about 4-fold. This means that per capita water use in the 1990s was slightly more than twice the level of 1900. In the richer parts of the world, water use stabilized after the 1970s through improved efficiency, motivated in part by anti-pollution regulations. In the United States, total water use peaked around 1980 and declined by 1/10 as of 1995, despite the simultaneous addition of some 40 million to the American population. While the world's thirst grew spectacularly in the 20th century, water was still used in the 1990s for much the same purposes and in much the same places as in 1900. Although industrial and municipal water use grew, irrigation still took the lion's share. The distribution of water withdrawals among the continents appears even more stable, as shown by Table 5. 2. Asia in the 1990s, as in 1900, used more water than all other continents combined. This comes as no surprise. Asia had more people than all other continents combined, and it had nearly 1/3 of all the world's streamflow. The only notable changes in the continental distribution of water use were the rise of North America's consumption, mostly in the first part of the century, and the smaller rise of South American water use, almost entirely post-1950. Within each continent, however, the patterns of water use changed a good deal, not least because of the rise of cities. Table 5.2 Continental distribution of water use, 1900-1990 Urban water. Cities always face the twin problems of procuring adequate drinking water and carrying off, or diluting, wastes. The simplest approach, dumping wastes in the nearest watercourse and drinking from it too, worked only where people were few and water plentiful. Early in human history, more complex approaches emerged, aiming to segregate drinking water from wastewater. Failure meant disease and early death for urban dwellers. New knowledge of the transmission patterns of cholera and typhoid concentrated attention on urban water quality toward the end of the 19th century. The stories of Istanbul, an old city with scant fresh water, and Chicago, a new city with plenty, illustrate the issues of urban water supply and urban sewage. Istanbul has a long history of sophisticated waterworks. Its situation, while strategic and spectacular, provided it with very limited fresh water in the form of a stream that flows into the Golden Horn, Istanbul's historic harbor. The city's population easily polluted this water supply to the point where it was dangerous to drink. Shortages of clean water constrained the city's growth. Engineers in Roman and Byzantine times erected dams and aqueducts and dug giant cisterns to address the problem. When the Ottoman Turks captured the city in 1453 and made it their capital, they built still more aqueducts, most of them during a great 16th-century expansion of Istanbul. Sinan, perhaps the greatest architect of his day, designed much of Istanbul's water system. With this infrastructure, Istanbul collected water from distances of 20 to 30 kilometers away, allowing it to become one of the world's largest cities by 1600. Its far greater growth in the 20th century required much more water. Consequently, while some of the Ottoman systems remained in use, Turkey, which emerged from the ashes of the Ottoman Empire in 1923, built several new dams and pipes, extending the reach of Istanbul to more than 120 kilometers. The new republic moved the capital to Ankara in the 1920s, which slowed the growth of Istanbul. But by the 1950s, rapid population growth throughout Turkey and rural exodus swelled the city by 10% per year. Most of the new arrivals built their own housing on the edges of the city and lived without piped water or sewage. These settlements sprawled in every direction in the 1960s and 1970s, and eventually their residents acquired enough political weight to extract favors, such as connection to the city water and sewage systems, from the government. After 1980, Istanbul drew heavily on water from the Asian side of the Bosporus, carried beneath the straits by pipe. Even this proved insufficient in the 1990s, when summertime often required strenuous water conservation. As in many cities around the world, water supply continued to vex authorities responsible for accommodating urban growth and ordinary people who had to make do with less. 5. Key locations in water quality history. Chicago is a young city on one of the largest lakes in the world. But it too developed water problems with its rapid growth in the 19th century. Its population used the lakefront and the Chicago River to dump its wastes, contaminating the water supply. What 30,000 Chicagoans dumped into the river and lake in 1848 caused only modest problems, but when the city's population boomed after the Civil War, old arrangements had to change. City authorities built longer and longer pipes out into the lake to try to draw water unsullied by the city, but Chicago's rapid growth continually outstripped the pipes. Until 1900, Chicago had a deserved reputation for typhoid. In 1885-1886 alone, 90,000 people around Chicago died of waterborne diseases. Typhoid sickened about 20,000 Chicagoans a year from 1891 to 1895. The epidemics provoked America's largest engineering project before the Panama Canal. The Chicago Metropolitan Sanitation District reversed the flow of the Chicago and Calumet rivers so that by 1900 they no longer emptied into Chicago's drinking water supply, but instead flowed toward the Illinois River and down to the Mississippi. Thus the sewage of Chicago, including the offal from the world's greatest stockyards, no longer menaced Chicagoans, but drifted away to Joliet, St. Louis, and New Orleans. Typhoid and other waterborne epidemics became only memories. The New York Times offered as headline news, "Water in Chicago River now resembles liquid." What suited Chicagoans did not always suit their neighbors. Residents of the other Great Lakes states, as well as the Canadian province of Ontario, thought the Chicago River reversal lowered the level of the Great Lakes. It did lower Lakes Michigan and Huron by 6 or 8 inches. Great Lakes states, the province of Ontario, and the U.S. federal government repeatedly sued Chicago and Illinois, as did St. Louis and other communities on the receiving end of Chicago's sewage. Under legal restrictions after 1930, Chicago and vicinity increasingly turned to groundwater, but by 1959 they overused it, provoking a lawsuit by the aggrieved neighboring state of Wisconsin. After 1985, larger deliveries from Lake Michigan eased the situation. So did Chicago's world-class sewage treatment plants, which cleansed its discharged water to a high standard. Getting enough water for growing cities was a problem that inspired ingenious solutions. Keeping that water clean, however, was another problem. One of the great divides among humankind that has arisen since 1850 separates those societies that provide safe drinking water from those that do not. Prior to 1850, pathogen and biological pollution plagued almost all urban societies and some rural ones. Great changes began in northwestern Europe shortly before 1850. Partly to combat diseases, London and Paris built sewer systems. These drained directly into the Thames and Seine, making both rivers putrid and lethal. Britain's Houses of Parliament once required burlap saturated in chloride of lime hung over their windows to protect the nostrils of MPs from the Thames stench. Following scientific discoveries about the contagion routes of cholera, typhoid, and other infections in the 1880s, Western European and North American cities built thousands of filtration plants to purify domestic water supplies. Hundreds of cities adopted chlorination, which kills most microorganisms, after Chicago's experiments with it in 1908 to 1910. Filtration and chlorination sharply lowered urban death rates. In the 1990s, waterborne diseases in the United States killed a few thousand unlucky people every year, a tiny fraction of their impact 150 years ago. 11. By 1920, almost all big cities in the richer parts of the world provided citizens with safe drinking water. Treatment of sewage took a little longer. Big cities on small rivers, such as Moscow and Madrid, quickly overcame the water's powers to assimilate organic wastes. Only primary sewage treatment, trickling through filters, took place until 1912-1915, when British engineers developed the sludge activation process. 12 In the 1920s and 1930s, big cities in the Western world began to build sewage treatment plants. Washington, D.C., acquired its first in 1934. Moscow built small treatment plants in the late 1930s and big ones in the 1960s. Tokyo's came after 1945. Technical refinements and expensive investments followed, especially after 1970, so that by the 1990s one could drink the effluent of many sewage treatment plants, which was often cleaner than the waters into which it flowed. 13. This notable success in containing lethal biological pollution spread unevenly around the world in the 20th century. At the other end of the spectrum, from the United States and northwestern Europe, people in parts of India and China suffered increasing pathogenic loads because cities grew while sewage treatment made limited progress. Colonial cities in Africa and Asia often acquired water filtration and sewage disposal systems in the European quarters, but not throughout the cities, creating different health regimes that corresponded to distinctions of wealth and race in places such as Shanghai, Kampala, or Algiers. In Calcutta, where filtration and sewage systems existed from 1870 in richer neighborhoods, the water system degenerated after 1911 when the capital of British India was moved to New Delhi. In Madras, the British left a sewer system built around 1940, but sewage treatment had to wait until around 1980. As late as 1980, half the world's urban population had no wastewater treatment whatsoever, and in China the proportion was 90%. In 1995, 89% of the residents of Greater Manila had no connections to any sewer system, 82% in Dhaka, and 80% in Karachi. By contrast, Mexico City left only 20% and Seoul 14% without sewerage. 14. The uneven history of the provision and treatment of urban water after 1880 was a case of escalating distinctions between the haves and have-nots. Those who had clean water and good sewerage got it because they were comparatively rich, and getting it made them healthier and richer still. Those who lacked it mainly because they could not afford it, and lacking it made them sicker and poorer still. Economists use the term increasing returns to describe situations in which the more you have, the more you get. The increasing returns generated by investment in clean water helped to create and widen the cleavages in wealth and health that characterize the world today. River water. Most urban water was river water. For millennia, rivers carried off human wastes, and the big rivers sufficiently diluted it so that little harm came from the practice. Until quite recently, there was not much the small populations of the Amazon or Congo. River basins could do to pollute the enormous quantities of water in those rivers. But rivers passing through thickly settled landscapes, rivers in the middle of industrial zones or mining zones, and small rivers acquired toxic loads of biological and chemical wastes in modern times. The Ganges. The Ganges drains a quarter of India. 15 Its basin in 1900 contained about 100 million people, of whom perhaps 10 million dumped their wastes directly into the river. The Ganges' fetid condition gave rise to one of the world's first anti-pollution societies in 1886. Mark Twain, who traveled the Ganges in 1896, found the water at Varanasi nasty on account of the foul gush of its sewers. By 1990, 450 million people lived in the basin, and some 70 million discharged their wastes into the Ganges. Almost all the sewage, in 1990 as in 1900, went untreated. Its decay robbed the river water of oxygen, menacing fish populations with suffocation. The Ganges, because of population growth, suffered probably 5 to 10 times more from biological pollution at the end of the century than at the beginning. The same must be true of hundreds of rivers around the world. But the Ganges is unique in one respect. It acquired pollution for sacred as well as profane reasons. In Hindu belief, gods created the Ganges to give people a chance to wash away their sins. Hindus believe that death or cremation at Varanasi ensures liberation of the soul, so Varanasi attracts millions of elderly and sickly Indians. In the 1980s, Varanasi's official crematoria burned 30 million bodies a year and deposited several million tons of human ash into the Ganges every month. Many additional bodies, partly cremated or not at all, were shoved into the river, as were roughly 60,000 animal carcasses. The Ganges was a bacteriological nightmare. When the first systematic pollution studies took place in the 1960s, it then got worse. Government cleanup efforts, begun in the 1960s and coordinated into the Ganga Action Plan in 1985, had little discernible effect. In the Ganges, the important changes were the intensification of bacteriological pollution, not problems derived from industrial emissions, which the river's huge flow masked until about 1990.17. Bathing in the Ganges may cleanse the soul, but, now more than ever, not the body. The Rhine. In the industrialized world, the situation was the opposite: chemical pollution, derived from technological change and economic growth, not from population growth, menaced rivers and lakes. The Industrial Revolution had a profound impact on the waters of the Western world, first in Great Britain. By the middle of the 19th century, factories dumped huge quantities of toxic effluents into British rivers. A royal commission in 1866 found that the water of the Calder, in northern England, made a tolerably good ink, which it demonstrated by using Calder water for a small part of the commission's report. The Bradford Canal, fed by water that had passed through the grimy city of Bradford, was worse. It was found practicable to set the Bradford Canal on fire, as this at times formed part of the amusement of boys in the neighborhood. They struck a match placed on the end of a stick, reached over and set the canal on fire, the flame rising 6 feet and running along the water for many yards, like a will-o'-the-wisp. 18. Some ameliorative measures took effect in the 19th century, but by and large the river and lake water of the industrial world received an ever larger and more varied chemical cocktail at least until the 1960s. The River Irwell, in 1869 caked over with a thick scum of dirty froth, in 1950 could be a vivid orange in the morning and jet black by noon. 19 A 1972 description of the Sumida River in Tokyo sounds like an updated version of the British Royal Commission report. As a result of the pollution, the famous events which once took place on the river, swimming, regattas, firework displays, have vanished. The gases rising from the river corrode metals, blacken copper and silverware, and shorten the life of sewing machines and TV sets. 20. Countless watercourses became variations on this theme. The story of the Rhine must stand for many rivers. The Rhine flows about 1,300 kilometers from the Swiss Alps to the North Sea. Before 1765, it flowed unobstructed, and its waters were clean enough to accommodate sensitive fish such as salmon, which were so plentiful that servants complained about having to eat it too frequently. As cities and population grew, urban wastes affronted sensitive souls, such as the poet Samuel Coleridge, whose visit to Cologne in 1828 inspired the poem Cologne. In Cologne, a town of monks and bones, and pavements fogged with murderous stones, and rags, and hags, and hideous wenches, I counted 72 stenches, all well defined, and several stinks. Ye nymphs that reign o'er sewers and sinks, the river Rhine, it is well known, doth wash your city of Cologne. But tell me, nymphs, what power divine shall henceforth wash the river Rhine? No power, divine or not, did much to wash the filthy, frothy Rhine for a century and a half. After 1880, mounting chemical pollution added to the mix. The proximity of coal and iron deposits in the Ruhr Valley assured that the Middle Rhine would in the 19th century become an industrial zone. By the 1890s, its iron and steel production was very competitive worldwide, and production levels climbed. The Rhine's suitability for navigation, its flow is very steady throughout the year, attracted other industries, including the formidable German chemical industry. By 1914, the Rhine's pollution load was heavy, salmon were rare, and the mayfish, whose upstream migrations once occasioned public festivals, disappeared entirely from the lower Rhine. The last sturgeon was caught in 1931. The Rhine got a brief respite with the wartime destruction and post-war stagnation of French and German industry, but recovery and Wirtschaftswunder worsened the river's condition. By 1980, about 20% of the world's chemical production took place in the Rhine basin. Metallurgical and chemical plants oozed copper, cadmium, and mercury into the river, and urban wastewater contained zinc, nickel, and chromium. Between 1900 and 1977, the concentrations of heavy metals in Rhine sediments increased 5-fold for chromium, 2-fold for nickel, 7-fold for copper, 4-fold for zinc, 27-fold for cadmium, and 5-fold for lead. Dutch hydrologists complained that German industry was metal plating Holland. No one complained, but the same was happening to the sediments of the North Sea. 21 French potash mining in Alsace helped sextuple the salt content of the Rhine between 1880 and 1960, jeopardizing the Dutch flower business, which irrigated its orchids and gladioli with Rhine water. Nutrient loading with phosphorus and nitrogen emerged as an additional problem after 1948, stimulating algae growth to the point that it clogged pumps and interfered with shipping. Algae's decay consumed oxygen, denying it to other species. New and toxic organic chemicals, such as DDT and PCBs, added to the brew, so that the Rhine between 1950 and 1975 was in its lower reaches almost devoid of fish, and fouler than ever before. Prudent sport fishermen threw back their catches in the 1980s, because Rhine fish often carried 400 times the concentrations of PCBs officially deemed safe to eat. 22 With high population, densely packed heavy industry and chemically dependent agriculture in its basin, the Rhine bore most of the pollution burdens a river can have. Cleanup efforts began with sewage treatment after World War II. In 1964, Germany required biodegradable detergents. International accords among Germany, France, and Holland restricted many forms of pollution from the 1970s. Most heavy metal concentrations in the river, but not the sediment, declined sharply after 1975. Fish populations, in decline since 1885 and especially since 1915, rose after 1976. More effective action followed the disastrous fire in a Sandoz chemical warehouse near Basel, Switzerland, in 1986. Firefighters sprayed water on the warehouse, washing pesticides, herbicides, and fungicides into the Rhine, killing virtually everything for 180 kilometers downstream. Although most of the aquatic biota recovered within 2 years, the affair concentrated the attention of ministers and captains of industry as never before. Regulations, incentives, and enforcement of all sorts followed. Fishermen caught salmon again in 1992.23. The Waterrace River and the Ashio Mine. Whereas the Rhine suffered from hundreds of industrial polluters, Japan's waterways river suffered from one, the Ashio copper mine in Tochigi Prefecture, active since 1610. During Tokugawa times, Ashio provided Japan with much of its copper, but had almost ceased production in 1877 when Furukawa Ichibai, a brilliant entrepreneur who had made and lost a fortune in silk, acquired the mine. He modernized and expanded operations, and in 1883 found a rich vein that made Ashio Asia's most lucrative copper mine. Japan's national policy of militarization needed Ashio because Japan imported 95% of its steel in the 1890s and Ashio's exports earned foreign exchange that helped buy the steel. Copper was Japan's second or third largest export, and Ashio produced some 40% of it. It was Japan's single most important mine. So authorities stood firmly by Furukawa. Furukawa's expansion and modernization brought far more serious pollution problems to the water and air around Ashio. By 1888, sulfuric acid rain from smelters had killed 5,000 hectares of forest and contaminated local waters. Floods became more common because hillsides lost their vegetation cover. Mine tailings seeped, or were dumped, into the nearby Waterways River, contaminating water used for irrigation in rice paddies. Local peasants became sickly and resentful. In the 1890s, death rates outstripped birth rates in the town of Ashio, which was home to about 30,000 people. Toxic waters killed off fish and fowl, depriving peasants of traditional supplements to their food supply. Everyone along the waterways knew it was Furukawa's mine that jeopardized their rice, their health, and their lives. Scholars, journalists, and the local member of the Diet, or Parliament, Shozo Tanaka, took up the cause, demanding that the mine and smelter shut down. Thousands of peasants marched on Tokyo 3 times, clashing violently with police and attracting publicity, which obliged the government to require Furukawa to install anti-pollution devices. But the technology was primitive and ineffective, so acid rain and river pollution continued. A fourth march on Tokyo provoked strong government repression in 1900. The Ashio mine was too important to the state to allow objections by its neighbors. The peasant anti-pollution movement lost all momentum with the patriotism and repression that attended the Russo-Japanese War. Miners rioted in 1907, a landmark event in Japanese labor history that was in part motivated by pollution grievances. 24 Some 450 Ashio households were banished to Hokkaido, Japan's northern island, ending popular protest. Thereafter, Ashio played its remaining neighbors in relative peace. Furukawa installed desulfurization equipment in 1955 and closed the mine in 1972. In a landmark judicial case, local farmers in 1974 won millions of dollars in compensation for a century of air and water pollution. The Waterways River Basin had served its purpose as a sacrifice zone in the industrialization of Japan. 25. Oued Fez, Morocco. More typical of the world's rivers was the Oued Fez in Morocco. 26. It had neither copper mine, nor chemical industry, nor holy status. But it had a city and farms along its banks. The Oued Fez flows through the city of Fez, on its way to the larger Cebu River and the Atlantic. Water supply and sewage systems were built for Fez in the 10th century. That left the Oued Fez clean upstream of the city and filthy below it. In 1371, Lisanan ibn al-Khatib, an intellectual from Granada, feeling sullied after an encounter with the people of Fez, wrote, "I entered the city as their water did, and I left it as it did." The impact of the city on the small river led rulers to build new cities upstream. The Marinids constructed a new upstream Fez in the 13th century. The French, who acquired control in 1912, did the same, yet further upstream. The pollution these efforts aimed to escape came from human wastes and from artisanal industries long established in Fez, such as leather tanning. From the 1960s, the Oued Fez also carried chemical fertilizer runoff from the Sayas Plain, just upriver from the city. By 1990, the water just downstream of Fez carried 5 to 10 times legal limits for several pollutants, and was perhaps 50 times as foul as in Ibn al-Khatib's day. A small river flowing through a sizable city in a poor country, the Oued Fez was highly vulnerable to pollution and ill-equipped to address it. In the 20th century, there were a few thousand rivers like it. Lakes and eutrophication. Cleaning up rivers, like resolving local air pollution, can be easy. Lakes, where polluted water may linger for decades rather than days, are another matter. In the 20th century, lakes in industrial areas acquired all manner of pollutants. In some cases, when downwind of smokestacks, they became acidic on account of acid rain. The most pervasive problem emerged in the 1930s, eutrophication. Every ecosystem has limiting factors that constrain life. In most bodies of water, either nitrogen or phosphorus plays that role. If somehow these limits are relaxed and unusual quantities of nitrogen or phosphorus become available, then aquatic plants and bacteria grow ebulliently. When they die, their decomposition consumes oxygen, which then becomes unavailable for other species. Vast changes in aquatic biotas often ensue. In extreme cases, all animal life suffocates for lack of oxygen. Algae population explosions can also render water unfit for drinking, swimming, navigation, and other uses. Warm water and stagnant water carry less oxygen to begin with than do cold and bubbly water, and thus are particularly at risk. Excess nitrogen and phosphorus usually came from urban sewage and, after the introduction of chemical fertilizers, from farm runoff. Eutrophication can happen naturally, as lakes age. But after 1850, human action more and more often drove the process. Urban lakes led the way. Lake Mendota, in Madison, Wisconsin, featured algal blooms almost annually by 1850. Lake Zurich in Switzerland suffered from eutrophication by 1898 and regularly after 1930. The Italian alpine lakes showed eutrophication beginning in 1946 and by the 1960s were occasionally covered by algal blooms. Small lakes near big cities eutrophied first because of the impact of human wastes. After 1945, phosphate additives in detergents aggravated matters, and even large lakes suffered from eutrophication. Seattle's Lake Washington illustrates the problem and a solution. Seattle's raw sewage caused eutrophication and small algal blooms in Lake Washington in the 1930s. The problem abated when the city diverted its sewage to Puget Sound in 1936. But in the late 1940s, suburban growth revived the problem, and by 1955 algal blooms decorated the lake. Political tussles ensued, but by 1963 the suburbs too sent their sewage into Puget Sound. Lake Washington cleared up again. Puget Sound size, regulations on phosphate additives, and improved sewage treatment prevented the Sound from suffering Lake Washington's fate. With the proliferation of sewage treatment in urban areas of Europe and America after World War II, cities reduced their nutrient loading of lakes and rivers. But the tremendous increase in chemical fertilizers more than made up for it. Runoff from fields and animal feedlots became the main source of excess nutrients. Simple solutions such as treating urban wastewater did not exist, short of abandoning chemical fertilizers. Hence eutrophication of rural lakes and watercourses spread widely, first in North America and Europe, and then in the 1960s and 1970s around the world, wherever intensive fertilizer use held sway. 27. In 1860, Chicagoans thought Lake Michigan was so large it could easily absorb the wastes their city might dump into it. Time proved them wrong. Similarly, most people living on the shores of the Black Sea or the Yellow Sea in 1900 gave no thought to problems that might arise from using the coastal seas as a sink for wastes. These seas appeared infinite for all intents and purposes. Time proved them wrong too. Today it is the deep oceans that are used as receptacles for all manner of wastes, on the theory that they are so huge they can safely dilute whatever human activity might inject into them. So far, that theory has held up. Seas and oceans. From the point of view of the deep seas and the oceans, the 20th century was much like any other. Human impact scarcely extended beyond the inland seas and the coastal zones. These, however, are important as they house most of the saltwater biota. 28. Absent churning tides, enclosed seas easily suffered from eutrophication. The Baltic Sea acquired the most severe case, visible by the late 1950s. The urban wastes of Stockholm, Helsinki, Leningrad, and Warsaw added to the farm runoff from increasingly chemicalized agriculture, loading the Baltic with excess nutrients. Arms of the Mediterranean, such as the Adriatic, recipient of the Po's nutrient-laced waters, bloomed with algae by the 1960s. So did the western Black Sea, courtesy of the Danube. Europe's inland seas suffered first because of the high urban populations and the early adoption of chemical fertilizers. But enclosed and shallow seas elsewhere soon felt similar effects. After 1970, eutrophication affected Malaysian waters for the first time. Wherever human action delivered excess nutrients, Red Sea, Persian Gulf, Yellow Sea, or Sea of Japan, coastal fisheries were affected. In some cases, the heightened fertility of the seas translated into more food for more fish, increasing the catch. But wherever nutrient loading generated severe algal blooms, fish stocks and catches plummeted. 29. Heavy metals flowed into the coastal seas and rained down upon them. An influx of marine heavy metals, apparent in sediments, took place in the Baltic after 1880 and on the southern California coast after 1940. Wherever metallurgy and chemical industries proliferated, heavy metals worked their way into the sea. The bays, estuaries, and enclosed seas of Europe, the USSR, and the United States received the heaviest doses, often sufficient to damage marine life. Cadmium and mercury accumulation sometimes made shellfish poisonous to human beings. 30 The most grievous case took place in southwestern Japan, in a fishing village called Minamata Bay. In 1910, Nippon Chiso built a chemical factory in Minamata, which gradually became a company town of 50,000 by 1950. From 1932, the Nippon Chiso factory manufactured acetaldehyde, which requires inorganic mercury as a catalyst. Nippon Chiso dumped mercury-laden waste into Minamata Bay. Bacteria converted the mercury into an organic compound, methylmercury, which worked its way up the food chain in ever greater concentrations. Unexplained fish die-offs began in the late 1940s. In the 1950s, the factory accelerated production and mercury dumping. Soon many Minamata cats went mad, danced as if drunk, vomited, and died. People called it cat dancing disease. By 1956, Minamata children began to develop brain damage. They had what would come to be called Minamata disease. 31 fish were correctly suspected, and soon fishermen found it impossible to sell their catch. A prominent local doctor, Hosokawa Hajime, confirmed that Minamata disease was mercury poisoning, but his findings were kept secret under pressure from his employer, the Chiso Company. In 1959, the local fishermen, unable to get the company to stop spewing mercury into the bay, attacked the factory. But the mercury kept flowing for another 10 years, while thousands of people developed symptoms, and more than 100 died. 32 The mayor, who consistently sided with Nippon Chiso, maintained in 1973, long after the connections between Nippon Chiso, mercury, fish, and death were clear, that what is good for Chiso is good for Minamata. The aggrieved mounted a lawsuit. The Chiso Company lost, and by 1977 had paid $100 million to Minamata victims and their families. For decades, no one from elsewhere in Japan would knowingly marry anyone from Minamata, on the theory that doing so might lead to deformed offspring. After 1984, the Japanese government dredged and, to its satisfaction at least, decontaminated the floor of Minamata Bay, which cost about $400 million. In 1997, authorities declared Minamata Bay free of mercury and removed the netting, installed in the 1970s, that had kept unsuspecting fish out of the contaminated waters. 33. The Minamata episode was probably the 20th century's worst case of contamination of the sea, but it was a simple one, involving only one nation, one factory, and one pollutant. A much larger and more typical case was the Mediterranean Sea, whose pollution history involved many nations and many pollutants. The Mediterranean. In 1798, Samuel Coleridge wrote, in the rhyme of the Ancient Mariner, "The very deep did rot, O Christ, that this should ever be. Yes, slimy things did crawl with legs upon the slimy sea." He wrote these lines 15 years before he laid eyes on the Mediterranean Sea. When he did, he served as secretary to the governor of British Malta for 2 years. The Mediterranean was good and slimy in only a few harbors. But 200 years later the deep did occasionally rot where algal blooms decayed. And from time to time slimy things did crawl or slither upon oily seas. The growth of modern industry in many Mediterranean countries, the emergence of chemicalized agriculture, and the rise in human and animal populations sharply increased the basin's pollution load after about 1950. A great deal of this ended up in the sea itself. The Mediterranean is the world's largest inland sea. In 1995, its catchment was home to about 200 million people divided among 18 countries. 34. It is a salty sea because evaporation is high and the freshwater inflow from rivers is low. At Gibraltar it's heavier, salty water flows out to the Atlantic underneath an incoming current of lighter, less salty ocean water. On average, it takes about 80 years for the Mediterranean to flesh out fully. Pollutants linger longer than in the North Sea, where they stay about 2 years, but not so long as in the Black Sea, where they can subsist for about 140 years. Biologically, the Mediterranean is at once rich and poor. It is rich in species diversity, home to about 10,000 animals and plants. But because its waters are normally thin in nutrients, its total biomass and biological productivity are extremely low. This is why, where it is not polluted, the water is so clear. In the 20th century, the waters of the Mediterranean grew progressively less clear and more polluted. Marine pollution, of course, is not new. The ancient harbors of Ostia, Piraeus, and Alexandria were strewn with wastes and garbage. Bays, estuaries, and inlets close to population centers, the Golden Horn, the Venetian lagoons, the Bay of Naples, were unsanitary long before the 20th century. It is possible that the amount of pollutants dumped directly into the Mediterranean is now less than it was a century or two ago. But pollution also reaches the sea via rivers and through the air, and in greater quantity than ever before. The main pollutants in the Mediterranean were and are much the same as elsewhere around the aquatic world. Microbes, synthetic organic compounds such as DDT or PCBs, oil, litter, and excess nutrients top the list, with heavy metals and radionuclides less important. In the most general terms, by 1990 about a quarter of the Mediterranean's total land-derived pollution contaminated the northwestern coasts from Valencia to Genoa, and a third plagued the Adriatic. Earlier in the century these proportions were probably higher. 35 The main sources were and are the big cities, big rivers, and a few coastal industrial enclaves. Microbial contamination from sewage existed in rough proportion to human population until the 20th century, because sewage treatment scarcely existed. By the end of the 20th century, about 30% of the raw sewage splashing into the Mediterranean received treatment, but the total quantity had tripled or quadrupled since 1900. 36 So the risks of gastrointestinal ailments, typhoid, or hepatitis to people bathing or eating seafood increased significantly. By the late 1980s, when the European Union had developed guidelines for permissible levels of microbial contamination, beach closings became routine from Spain to Greece. In any given summer in the 1990s, about 10% of Mediterranean European beaches failed EU standards, although they were not necessarily closed. Oil, a negligible pollutant before 1900, became a major one with the energy transformation of the 20th century. The emergence of the Persian Gulf oil fields after 1948, the existence of the Suez Canal, and the energy demand of European transport and industry assured that the Mediterranean would become one of the world's oil highways. The Mediterranean has yet to endure a major tanker spill, although it has suffered many modest ones. Offshore oil drilling, a major pollution source elsewhere, remained tiny in the Mediterranean. Most oil pollution came from routine operations, unregulated until the 1970s, such as cleaning out tanks and dumping bilge water. The quantities involved were minor before World War II because the oil trade remained small. During the war, routine shipments were suspended, but a large share of military shipments were sunk. Nonetheless, oil pollution only grew after the war, driven by the huge expansion of European demand for Middle Eastern oil. About a quarter of the world's oil shipments crossed the Mediterranean in 1990. A 1975 estimate calculated that 500,000 tons of oil leaked into the Mediterranean each year. Another in 1980 to 1981 suggested about 820,000 tons. Typically, one-third of it washed up on shore as tar, which plagued Mediterranean beaches more than any others in the world. Much of the rest floated atop the water as oil slicks, which at times thinly covered as much as 10% of the sea's surface. Around 1980, the Mediterranean absorbed a sixth of the world's oil pollution. Over half of this took place in routine loading and cleaning. Libyan waters were most affected. 37. Industry contributed more to sullying the Mediterranean than oil. Many factories sprouted on the water's edge, taking advantage of the low costs of seaborne shipping. Others emerged on rivers that flow into the sea, for transport reasons or because industrial processes required fresh water for cooling or cleaning. Even factories far from the water polluted the Mediterranean via airborne deposition. Whatever the avenue, the sea received significant amounts of synthetic compounds and heavy metals from industry. Industrialization proceeded spectacularly in the Mediterranean basin in the late 20th century. Mediterranean